Yes.
My second half didn't have chapter 14 in it.
Oh yeah, you have to go back to the first
I didn't
half.
actually realize that until after the test.
Okay. Yeah. It's in the previous edition. Yeah, it's split up like that. Well, this is chapter 16. What we're doing right now, because we left on, what was it, step 4? We left off? We left off at step 4, which is H3PO4 plus water. The strongest acid, H3PO4, the strongest base, water, uses hydronium dihydrogen phosphate. We look at this. This is like chapter 16. You know, chapter 16 is like a triprotic acid, like phosphoric acid and water. And so here we look for all hydronium ion producers. So we got a lot of steps left to go. Did we get here?
Yeah.
All right.
Step 5.
We got to step 5. So we already finished step 4?
Yeah.
All right. Then let me jump to step 5. Step 5 was dihydrogen phosphate?
Yeah.
All right. And so this is just the triprotic acid and water. Did I make a mistake with the hydronium? Did I put the hydronium initial here?
Yeah, you did.
I did? All right. In step 4.
Yeah, in step 4 and 5.
Okay, good. Yeah, it's a common ion. Other than that, this is like chapter 16. The only difference in chapter 16, this would have been 0 and 0. All right, so we go on to step 5. Step 5 would be the next hydronium ion producer, which we do the dihydrogen phosphate. Dihydrogen phosphate plus water. Since this is an acid solution, we only look for hydronium ion producers. We don't care about the hydroxide ion producers. HPO4 2 minus. All right, so looking at this, H2PO4 minus has a Ka value of 6.3 times 10 to the minus 8. So we'll use that. How far did we get in this one?
We found X, I think.
Okay.
1.2736 times 10 to the minus 9.
Times 10 minus 9?
Yeah.
That's very small. And so we're going to barely add any hydronium to this. But if we're doing an inventory, then we need to figure everything out. So what will be the equilibrium of that dihydrogen phosphate? What was the initial here? Minus X.
5.51 times 10 to the minus 4.
5.51 times 10 to the minus 4?
Yeah.
Okay, minus X?
Yeah.
All right, so we'll just do that. In fact, if you look at this, this is 10 to the minus 9, and it's 10 to the minus 4. So really, we aren't going to lose much of the dihydrogen phosphate. And this is largely due to how much hydronium is here initially. How much hydronium do we have right now?
2.6836 times 10 to the minus 2nd.
Yeah, that's quite a bit of hydronium, plus a little bit more. 10 to the minus 2nd plus 10 to the minus 9. 10 to the minus 9 is not really going to have much impact. And then this one, we started off with 0. So we're going to end up with 1.3726 times 10 to the minus 9 molar here. Now, the thing we got to check for here is this. And so, actually, let's go ahead and calculate the concentrations first. Check it. Just a second. So 5.51 times 10 to the minus 4 is just going to be 5.51. We can do it on the calculator. 5.51 times 10 to the minus 4 minus 1.3726 times 10 to the minus 9. This gives me 5.50998 times 10 to the minus 4. And so we're going to lose a tiny bit, not much. And then over at the hydronium over here, that's just going to come it's going to be 7 digits, so we aren't even going to see it. 6836 times 10 to the minus 2. And this will be 1.3726 times 10 to the minus 9. All right, what we'll do is we'll double check to make sure that these satisfy K. So take my this one and invert it. Times 2.6836 times 10 to the minus 2 times 1.3726 times 10 to the minus 9. I get 6.6. I'm off. When I do the double check, I got 6.68 times 10 to the minus 8. In other words, 6.7 times 10 to the minus 8. It's supposed to be 6.3 times 10 to the minus 8. Is that what we used, 6.3, or did we use the one off the board here?
I got like 6.2.
You got 6.2 when you... I'm sorry?
For my double check.
Oh, you did?
But let me check.
Maybe I miswrote the numbers. Three, 7, 2, 6.
Oh, for X, it's 1.2736, not 1.
Oh, okay, 1.2, thanks. Let me recalculate this one. Insane. All right, so it comes out okay. 6.2 is what you got?
Yeah.
6.2 what?
Hold on.
Let me just do this. 1.2726 times 10 to the minus 9 times 2.6836 is 2. 6.19. 6.198 times 10 to the minus 8 is what I got. We might have used this one, though, the other value here. H2PO4 minus, did we use the 6.23 times 10 to the minus 8? Or did we use the 6.3?
It's 6.3.
Yeah, we're off.
Well, that answer is pretty close to 6.2.
We're off. You got to go back and look. I mean, it's close. You know, 6.2 versus 6.3. It's close, but a little off. And so we could go back and try to clean it up, carry extra digits or do whatever. But it has me worried. The only thing is it didn't really impact. I mean, there's barely any addition here. And so does step 5 perturb step 4? You have to ask yourself. Did step 5 perturb step 4? Did we significantly change the dihydrogen phosphate or the hydronium? No. And so step 5 really doesn't perturb step 4, so we could do this stepwise, right? Stepwise fashion. It should be okay. And so let's go to step 6. Step 6, this is a triprotic acid. This triprotic acid, we can go to HPO4 2 minus. HPO4 2 minus is going to also produce hydronium. It's going to give us some H3O plus PO4 3 minus. Now, if we're thinking about producing hydronium, is it going to really produce very much hydronium? Well, let's look at the K value. It's 4.2 times 10 to the minus 13. 4.2 times 10 to the minus 13, which tells me that it's going to barely produce any hydronium. But if we're doing the inventory, then we want to know how much phosphate we're going to generate in this particular step. And so we're going to go ahead and calculate it. And so I'm going to carry down the monohydrogen phosphate concentration. It's 1.2726 times 10 to the minus 9. Water is a liquid. Hydronium is 2.6836 times 10 to the minus 2. And phosphate, 0. So the change is going to be a very small change. I mean, look at the K value, plus X molar, plus X molar. So at equilibrium, we're going to have 1.2726 times 10 to the minus 9 minus X. 2.6836 times 10 to the minus 2 plus X, and then X. Usually I just write these in decimal, especially this one here. Easier than scientific. Anyway, we've got to solve this for X. So this is going to equal the hydronium total so far times the phosphate divided by the monohydrogen phosphate. It's going to come out 2.6836 times 10 minus 2 plus X times X divided by 1.2726 times 10 to the minus 9 minus X. What we'll do is I'll just do the simplifying assumption here. Do the simplifying assumption. We'll end up with 2.6836 times 10 to the minus 2 divided by 1.2726 times 10 to the minus 9 times X. So X is just going to be here 1.2726 times 10 to the minus 9 times 4.2 times 10 to the minus 13 divided by 2.6836 times 10 to the minus 2. 1.99 times 10 to the minus 20. And so the assay is valid. I mean, the percent change is going to be way less than 5%. The percent change is going to be the change, which is 10 to the minus 20 over the initial. This is the smaller initial, which is 10 to the minus 9 times 10 squared. So this is going to be way less than 5%. And so the simplifying assumption is valid, which is often the case when you have a common ion like this. Well, this is 10 to the minus 20. So we have 10 to the minus 9 minus 10 to the minus 20. That's not going to have any impact on this. So this is just going to be about 1.2726 times 10 to the minus 9. And this is 10 to the minus 2 plus an additional 10 to the minus 20. It's going to have no impact here. And so the simplifying assumption is very valid in these cases because compared to the initial, the change was minimal. However, over here, the change is significant because we're starting off with nothing, 0. If we have 0, then this change is significant. It's going to be 1.99 times 10 to the minus 20 molar. You know, it's a minuscule amount of phosphate, but it's significant compared to 0. So that's why we have it here. Let's go ahead and double check this to see if I didn't screw up the calculation. Times 2.6836 times 10 to the minus 2 divided by 1.2726 times 10 to the minus 9. 4.2 times 10 to the minus 13. So the double check is good. It's good. So that's right on. And so basically, you know, after all those steps, 3 steps, we end up with phosphoric acid in water. Well, that's like a chapter 16 problem. The only difference is we're starting off with so much hydronium from the previous 3 steps. And so we do Ka1, which is step 4, Ka2, which is step 5, and Ka3, which is step 6. And we did the 3. Now, there's only one step left. What is it?
Okay.
KW. KW is the final step left. KW, well, let's figure KW. But before that, let me do a quick aside. If you look at step 4, 5, and 6, you know, that's K1, K2, K3. And so the question is this. Could I have shortened my calculation by combining steps 4, 5, and 6? Could I have combined steps 4, 5, and 6? Okay, what I'm talking about is this. If I take H3PO4 plus water, this is going to give me hydronium. Yes. And so this would be Ka1. And then H2PO4 minus plus H2O liquid here gives us hydronium. And HPO4 2 minus, this is Ka2. And then Ka3 would just be HPO4 2 minus plus water liquid gives us hydronium and phosphate. This is Ka3. And then what I do is I just combine these three. If I combine these three equations, I'm going to get H3PO4 plus 3 waters yields 3 hydroniums plus a phosphate. And then the K for the combined is just equal to Ka1 times Ka2 times Ka3. And could I just have combined those three and just did one ice table instead of 3 ice tables? This way, I would need only 1 ice table. Rather than 3. And so this is very appealing because I could save, you know, that's a lot of steps. I mean, we're already on step 6. It's getting crazy, the number of steps. But here, if I can combine these 3 into 1, then I'll just do 1 ice table here. But unfortunately, the answer is no. I can't do this. I can't do this because of these species. You know, I can't do this because it assumes that all the phosphate ends up only in phosphoric acid and phosphate. There's no dihydrogen phosphate, and there's no monohydrogen phosphate. And so this assumes all phosphate is in H3PO4 and PO4 3 minus. And so here, there's no dihydrogen phosphate in this equilibrium. There's no monohydrogen phosphate in this equilibrium, so I can't use it because I'd be missing those 2 species. I can't assume that all the phosphates only going to end up in phosphoric acid and phosphate. So, does that make sense? And so I'm missing some species in my equilibria, missing important species. So I can't use the combined. So I had to do it step 4, 5, and 6. And so now I'm at my final step, fortunately. The last hydronium ion producer is going to just be water. KW. It's not going to produce much hydronium. And so this is going to be step 7, which is going to be H2O liquid plus H2O liquid. This is going to give me hydronium and hydroxide. Okay, water is pure liquid, so ignore those. Hydronium, I'm just going to write it as 0.026836. Hydroxide, 0 molar right now. If I look at this, you know, what's the most hydronium I'm going to get from KW? The most hydronium we'll get from KW is 10 to the minus 7. And since this is a common ion, I'd expect a lot less than 10 to the minus 7. Will 10 to the minus 7, or actually 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar hydronium be significant compared to our initial? No. And so the amount of hydronium I'm going to add is minimal, but I will add a significant amount of hydroxide. So let's go ahead and calculate that. So this is going to be plus X molar, this is going to be plus X molar. So I'll end up with 0.026836 plus X molar and then X molar. And so, you know, we know KW is equal to the hydronium times the hydroxide. So it's 0.026836 plus X times X. Then we're going to use a simplifying assumption here, 0.026836 times X. X is equal to KW, which is 1 times 10 to the minus 14, which is 1.0 times 10 to the minus 14, divided by 0.026836. Calculator. It's not really necessary. 3.72 times 10 to the minus 13. 3.72 times 10 to the minus 13 is nothing. The initial is 10 to the minus 2. I mean, excuse me, the change is 10 to the minus 13. The initial is 10 to the minus 2 times 10 squared gives us a 10 to the minus 13% change, which means that the essay is valid. So this is going to come out to 0.26836. Again, no impact really on this, but there's going to be a big impact here because there's nothing. So this is going to be 3.72 times 10 to the minus 13 molar. Let's go ahead and double check this calculation. So times 0.026836, and we get 1 times 10 to the minus 14. So double check is good. And then we look, did this perturb the previous step? Did it perturb the previous step? No. I mean, the hydronium barely changed at all, so it didn't perturb the previous step. So stepwise was successful here because none of these steps perturbed the previous steps. So what we do is this. If we were only interested in pH, where should we have stopped? If we're only interested in pH, where should we have stopped? At step 6? Okay, because beyond step 6, nothing changed really in the hydronium. So up until step 6, we had a change. Well, I don't know about step 6. Look at step 5. What was the hydronium in step 5? It was the same, right? And what about in step 4? What was the hydronium in step 4? How did the hydronium change in going from step 4 to step 5?
Got slightly smaller.
It would have gotten slightly bigger. Going from step 4 to step 5, it should have gotten slightly bigger. Did it? No, it got smaller? Really?
I don't know if you get bigger,
Yeah. Okay, so we probably should have stopped by step 5. If we were interested in hydronium only in the pH, step 5 would have been good. If we're interested in the inventory, then we have to do all the steps. And so at step 5, at step 5, you know, phosphoric acid is pretty strong for a weak acid. So we should have known, you know, we had a mixture of strong acid, hydronium, and a pretty strong weak acid, phosphoric acid. So probably the phosphoric acid is going to contribute. Now Petrucci says that if you have a strong acid and weak acid combination, you could ignore the weak acid. In this case, we couldn't ignore the weak acid because it's a fairly strong weak acid. Does that make sense for that? A little bit? All right, so now let's figure out this is the final hydronium. So all the steps combined leads to this cumulative hydronium here. This is the final hydroxide. And so what we'll do is we're going to inventory this. So, you know, when we did this mixture, this is what we're going to end up with. The hydronium is 0.026836. This is too many sig figs, but we'll go ahead and we don't round it until the final answer. The final answer is pH. So we want to know the pH of this. So negative log of 0.026836 is 1.57. Did the buffer work very well? You think the buffer worked very well? The buffer was a pH 7 buffer, and so the 1 drop of 6 molar HCl dropped the pH from 7 all the way down to 1.57. The buffer didn't work very well, and the reason the buffer didn't work very well is because we exceeded the capacity of the buffer. You know, we didn't have enough base component in the buffer to neutralize it, and therefore the pH is going to change much more dramatically, as we saw here. So the pH changed significantly. Okay, but we also have hydroxide in here. You know, this is a very acidic solution, so the hydroxide should be very small. We have phosphate in here. This is the cumulative total of phosphate. Hydronium, this is not, because the hydronium passes down to the next step. But monohydrogen phosphate, this is the end of the line, so all double boxed ones we have. And then you go back up. As we go back up to step 5, at step 5, we're going to have the dihydrogen phosphate, final concentration. At step 4, we'll have the phosphoric acid concentration. And so this is kind of just like a phosphoric acid solution. What's going to be present here is H3PO4, H2PO4 minus, HPO4 2 minus, and PO4 3 minus, as well as hydronium and hydroxide. So this is kind of like at chapter 16. We ended up exceeding capacity. We ended up making phosphoric acid and then figure out what we had left. And so those concentrations we can get from the previous steps here. I'll let you sort those out. All right. Well, anyway, this is kind of long and it seems confusing, but really it's the same step over and over again. And the same step over and over again is strong acid plus strong base. The confusing thing comes when we want to take shortcuts. When we want to do shortcuts, then you have to keep, you know, those clear, how to use those shortcuts. Because if we don't want to take any shortcuts, then it's a repetition of steps. Strongest acid plus the strongest base.
So the simplifying assumption means that when K is below 10 to the minus 10, or 10 to the minus 10.
No, I use it. I try to use it even at 10 to the minus 3, 10 to the minus 4. It just depends on the initial.
Okay.
Yeah, you could. I know the book says 10 to the minus 10, but if you have a high enough concentration, it's 10 to the minus 3. It could still work. And so what I do is, it doesn't take much time to do it. The book says to do a calculation. The book says to do a calculation, which is take the ratio. But you know, I don't bother taking the ratio because why do that? Why not just calculate it using the simplifying assumption? Because it takes as much time. It takes just a fraction of a bit of more time, but you know, and so I don't bother taking the ratio. I don't bother thinking about it. I just do it. If it fails, that's fine. You know, I'd rather just do it and see that it fails than take a ratio and guess. Is that ratio big enough? Is that ratio small enough so that it works? So I don't like the book's method in saying, okay, it's 10 to the minus 10, because that could fail. That's like 90% of the cases, it works, right? The 10% is going to fail. So why even bother? Because there's a chance it might not work. I mean, it might give you the wrong answer. The ratio is good. I mean, the ratio is good when it's good, but when it's bad or it's borderline, then you spend too much time thinking about it, and it's not even worth it. You just try it and see. That's my philosophy towards that. All right, so that was buffers. So buffers, you know, we have a strong acid, strong base, and they're conjugates. And we have the Henderson-Hasselbalch equation for buffers. And so the Henderson-Hasselbalch, you got to recognize, you know, when we'll have buffers and when we won't have buffers. The next series of calculations we're going to do are titrations. For titrations, you know, we have the titration curve that we looked at the other day. You know, let's just see the behavior. You know, if we look at a strong acid, an example would be like HCl plus a strong base, like sodium hydroxide. Then the titration curve looks like this. You know, we're going to have different regions. A strong acid is going to start off at a low pH, you know, between 1 and 2 or something like that. You know, if this is 0.100 molar HCl, we'll start off at pH of 1. And then as we start adding the sodium hydroxide, what happens is, you know, the sodium hydroxide will neutralize some of the acid, but basically we'll just have excess HCl until we completely neutralize it because we don't have enough sodium hydroxide. Once we get enough sodium hydroxide to completely neutralize it, then the pH shoots up. The pH is going to hit 7, you know, because here we're going to form sodium chloride, salt and water. And then what happens is, once we've neutralized all the acid, then we have excess base. If we have excess sodium hydroxide, the pH is very high. And it's going to plateau out. It's not going to get all the way to 13 or 14 because of solution dilution. But this is what the pH titration curve looks like. And the equivalence point should come at pH 7. Sodium chloride's a neutral salt, and we produce salt and water. And so the reaction here is HCl plus sodium hydroxide yields sodium chloride plus H2O liquid. The only difference is, you know, we do this in terms of chapter 17. So we would do this in terms of an ice table rather than a Chem 1A stoichiometry problem. And so if we start off with 0.100 molar HCl, and let's say we didn't neutralize it, we only added like 0.50 molar, 0.050 molar, then it's not all going to be neutralized. Now K is going to be very large for this, so we're going to neutralize half of it. So we're going to get 0.050 molar, 0 molar, and 0.050 molar here. Well, sodium chloride's a neutral salt, so that doesn't have any impact. And so what we're left with is HCl. If we have an HCl solution, that's a monoprotic acid. If we've got a monoprotic acid, then the hydronium ion producers are going to be HCl and KW. And so we would do a second step here. Actually, we would do, you know, technically this is the way we do it in Chem 1. We might do a step I. Do you remember step I? Step I. Solution dilution, and then we'll go to step 1. And then step 2 would be take the strongest acid. The strongest acid left over is HCl. This is the strongest base, which would be water. This is going to form hydronium and chloride. And so we just drop it down here. This is 0.050. This is 0.050 here. Water. It's going to be 0. Water is pure liquid. All right, K is very large for this, so it's going to be complete. 0, 0.050, and 0.100. And then we have KW. Should I bother with KW? If I'm interested in pH, should I bother with KW? Well, what's the most hydronium I'm going to get from KW? The most. The most hydronium I'm going to get is 10 to the minus 7 molar. That's like in pure water. And so if I get 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar, is it going to have any impact on this? This is 10 to the minus 2. No impact. And so this is going to be about the same. And so if I was interested in pH, I wouldn't bother doing KW. I have so much hydronium in here, as is, it's not going to change it. And then I calculate the pH. So let's calculate the pH here. pH is going to be negative log of 1.3. So about, you know, I neutralized about half of it. The pH went from 1 to 1.3. You know, the pH has barely climbed a little bit. It's not until I get very close to neutralizing all of it, the pH skyrockets. And the pH is going to skyrocket a huge amount here. We're talking about, you know, 7, 8 pH units. And so this is a huge rise in pH here. And so we could calculate any point in the titration curve by just doing this and then seeing what's left over, because if I add a stoichiometric amount, 0.100, 0.100, I'm just going to be left with sodium chloride. The pH of sodium chloride is 7, it doesn't hydrolyze water. If I have more than 0.100, let's say I have 0.100, 0.150, then I'm going to have 0.050 molar sodium hydroxide. I calculate the pOH and I get that, and it's going to be up here, 12 to 13 range. And so I would just do ice calculations like this. All right, that's for a strong acid, a strong base. This is a Chem 1A style titration. But what we're going to look at next is a weak acid. Weak acid. Let's go with a weak acid like acetic acid. And the base. We do a weak acid like acetic acid, then the titration curve looks similar, except a weak acid is going to have a higher pH. So rather than starting at 1, it starts in the 2 to 3 range, let's say. So we're around here, weak acid. In fact, we could calculate what the starting pH is. If we do a 0.100 molar acetic acid, that's like a chapter 16 type problem. This is 0 milliliters of titrant. On the x-axis, we have the sodium hydroxide, which we're going to do. So we're going to titrate our acid like this with sodium hydroxide. And so we'll put our acid here, 0.100 molar acetic acid. Now, this is a chapter 16 style problem, so let's go ahead and just calculate what is the pH of 0.100 molar acetic acid. So we look for all the hydronium ion producers. So we're going to have acetic acid plus water yields hydronium and acetate. I'm going to use abbreviation for acetate, AC. Ka for this is 1.8 times 10 to the minus 5. All right, so we have 0.100 molar, and the water is pure liquid. This is going to be 0, this is 0, so nothing's happened yet. So we're going to get minus x plus x plus x. So we're going to put 0.100 minus x, x, and x molar. So this is going to be the hydronium times acetate, which is going to be x squared divided by the acetic acid, which is 0.100 minus x. Now this is 10 to the minus 5, but you know what I'm going to do? I'm going to try the simplifying assumption regardless, because it doesn't take long. You know, that's going to give me x squared over 0.100. And so this is going to be 1.8 times 10 to the minus 5. Times 0.1 divided by, well, not divided by anything. Let's take the square root of that. 1.34 times 10 to the minus 3. All right, now, you know what, I'm going to have to do it. I'm going to have to look at the percent change here. The percent change is going to be the change, which is 0.00134 over the initial, which is 0.100. So if I look at it, it's a 1.3% change. This is a 1.3% change. And so it's okay, you know. If it's starting to get closer to 5, I'd probably use a quadratic. But 1.3, it's kind of big, but it's okay. And so we'll just go with that then. This is going to be 0.100 minus point. You know what? Since we're only interested in pH, you know, I'm going to do this just for the double check, just to make sure it worked out. All right, so let's just go ahead and double check these. So I'm just going to square that divided by 0.09966. Using 1.8 times 10 to the minus 5, 1.81, 1.0806. So it's okay, the double check's okay. So we're good. Now I got to worry, you know, there's another hydronium ion producer because this is acetic acid. If I have acetic acid, we have the acid's going to be hydronium producer plus water. Should I worry about Kw? Well, let's look. How much hydronium do I have here? I have 10 to the minus 3. Water at the most is going to give us 10 to the minus 7, but likely it's going to give us less, 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. Is that going to make any impact on this? Will it make any impact on this? No, therefore I'm going to ignore Kw.
For Kw, once you have the hydronium concentration, can you just use the assumption that pH plus pOH always equals 14?
Yeah.
And then, yeah, just calculate pOH.
Yeah. We could do it that way too. But the thing is, if I was interested in inventory, I have to do Kw. I would need to do it, but if we're only interested in pH, I'm just going to do this. And so we'll say that Kw is going to be a negligible contributor of hydronium to this. And so what I'm going to do is I'll just take the negative log of 0.0134. And so the pH is 2.87. I'm actually only allowed 2 sig figs, so the pH is 2.872. Kw is negligible. Negligible H3O plus. It's significant for hydroxide. So I'm actually wrong here. It's 2.8 around there. 2.87. And so our first measurement here is 2.87. Our first calculation here is our initial pH before adding any sodium hydroxide is 2.87. Now let's say that the base is 0.100 molar. If the base is 0.100 molar, then and the acid is 0.100 molar, then it depends on how many milliliters we have here. And so let's go with 10.0 milliliters here. That means if I have 10.0 milliliters of 0.100 molar acetic acid, how many milliliters of 0.100 molar sodium hydroxide will it take to neutralize that? Well, the same concentration, so it's going to take.
Less?
No, it's actually going to take 10.
Doesn't the acetic acid only partially ionizes?
It only partially ionizes, but the thing is, that's with water. With water.
Oh, so the acid goes to complete reaction.
Yes. Yeah. You know, there's going to be a tug of war with water, but once you throw in sodium hydroxide in there, forget it. It's going to completely, and so completely react. So it's going to go to 10. At 10.0, we expect it. So what happens here is the pH goes up a little bit. We call this the excess acid region earlier, but it's a little bit more than that excess acid. Essentially, we have excess acid, and then when we get to 10, then we should neutralize that. The pH rises, and then we're in the excess base region. Now, this excess acid region is interesting because of what we form here. So let's take a look at this excess acid region in more detail. Then here we've neutralized it at this point. The neutralization point is going to be the middle of this rise here. And then this is the excess base region. Now, the excess acid is a mixture, actually. And so let's take a look at a point here. Where should we go in here? How many milliliters do you want to go? Pick a number of milliliters. All right, let's go to 5 milliliters here. Neutralize like half of it. I'll try to keep things at 3 sig figs. You would have more because in titration you'd have 4. Actually, no, we'll just go 4. Maybe more realistic. So, at 5 milliliters, this is what we have. And so what we're going to do is we're going to just add 5 milliliters from the base burette to this. And so we'll call this, this is our first calculation. We'll call this calculation A here. Now 5 milliliters, we'll call this calculation B here. Calculation B here, we're going to add 5 milliliters to the 10 milliliters that's already there. So the total, how many milliliters will we have? In total, we're going to have 15.00 milliliters. So we have 15.00 milliliters. What's the first step we do? First step we do is step I. Step I stands for solution dilution. And we do solution dilution before doing any reaction. So we got to figure out the new acetic acid concentration. Well, it's a 10.00, that's what we started with, to 15 dilution. So it's a 10 to 15 dilution of 0.100 molar. And so this is 2/3. 2/3 is 0.066. So actually 2/3, I'm going to get 3 sig figs. 6. We'll just go with carry extra, 1 extra. So quadruple 6. Smaller. All right, that's acetic acid. Then we're going to go with the sodium hydroxide concentration. The sodium hydroxide, we just put in 5 milliliters and diluted it to 15. And that's 0.100 also, molar, 0.1000. I'll just go with 3 sig figs. So that's going to be 0.03, it's a 1/3 dilution, so 0.03333 molar. All right, this is step I. Step I is the solution dilution, which comes from here. And then we go to step 1. What step 1 consist of? It's always the same. Step 1 would be the strongest strongest acid plus the strongest base. What's the strongest acid present? The strongest acid present is going to be acetic acid. The strongest base present is sodium hydroxide. So acetic acid plus sodium hydroxide is going to make sodium acetate and water. What's K for this? Not just very large.
Very, very large.
Very, very large. Very, very large. All right, so the acetic acid concentration from step I is 0.0 quadruple 6. The sodium hydroxide is 0.0 quadruple 3. And sodium acetate is 0. And so the change here is going to be complete. And so we're going to end up with 0.0 quadruple 3 and 0 and 0.0 quadruple 3. Because the limiting reagent is the sodium hydroxide here. All right, this is the end of step 1. The water is a liquid. Now we go on to step 2. Step 2 is take the strongest acid remaining. What's the strongest acid remaining? Acetic acid. Plus the strongest base remaining. Well, there's no more sodium hydroxide. And so what's the strongest base that's left?
Water.
Not water. There's a stronger base than water left.
Sodium.
Sodium acetate. The acetate's the strongest base. And so if we take the strongest acid remaining, which is acetic acid, and the strongest base, sodium acetate, we get acetic acid plus sodium acetate. But acetic acid plus sodium acetate, you know, step two is acetic acid plus sodium acetate yields sodium acetate plus acetic acid. So is there any change there? There's no change there. But you know, you've seen this before. You have to recognize this. Do you recognize that this is a solution of acid and base? A solution of acid and base, weak acid plus weak base, is also called a buffer. And so you have to recognize that, hey, wait a minute, I don't need to do this. Because you might try to do acetic acid in water, but if you do acetic acid in water, then you got to worry about the sodium acetate. This is a special case. This is what we call an HH buffer. This is an HH buffer. HH stands for what? Henderson-Hasselbalch buffer. It's a Henderson-Hasselbalch buffer because we have weak acid and weak base in significant concentrations, and they're conjugates of each other. And so I can stop here, because in a Henderson-Hasselbalch, Kw should not be significant here. And so the pH is just going to equal the pKa for HAC plus the log of the base, which is acetate, over the acid, which is acetic acid concentrations. These are the initial concentrations. The initial concentrations will be here. That way I don't have to do an ice table for step 2. And so the pKa, well, it's going to be, the pKa, I know the Ka. The K is 1.8 times 10 to the minus 5. So the pKa would be the negative log of that, plus the log. Now the concentrations here are going to be 0.0 triple or quadruple 3 over 0.0 quadruple 3. And so this is the log of 1. The log of 1 is 0. And so what is the log of 1.8 times 10 to the minus 5, the negative log of that? And so the negative log of 1.8 times 10 to the minus 5 is 4744. And so this here, this pH is 4744. And so this is actually a mixture. This is the excess acid, acetic acid, plus its conjugate base. Mixture. In other words, this is HAC, AC minus, is what we're always going to end up with. We're always going to end up with this because the sodium hydroxide is going to completely react, leaving us, because we have excess acid, leaving us with an acid plus conjugate base mixture. In other words, we call this region buffer. This is the buffer region. And so the buffer region is going to extend out here. So we could do any, you know, any amount of sodium hydroxide in the buffer region and then calculate it. But there's something called the buffer range. Do you recall what the buffer range is? The buffer range is, we don't want to go beyond plus or minus 1 of the pKa. And so the buffer range for acetic acid, acetate, would be 374 to 574. That would be the buffer range. But the buffer range is for practical application of the buffer. And so the buffer range, you know, to make a a practical buffer using this system, we wouldn't want to go beyond 374 to 574. Because what would happen if we go beyond 374 or 574? Well, it would be too lopsided. You know, lopsided meaning too much acid, too little base, or too much base, too little acid. And so the optimum range is between 374 and 574, which is about here to about here. You know, 374 to 574. This would be the optimum range. Do you see how flat it is in this optimum range? However, with the Henderson-Hasselbalch, we can extend out. You know, beyond this, we can use the Henderson-Hasselbalch to almost here, to within drops. You know, this is like 1 drop or less than 1 drop. And so we could use the Henderson-Hasselbalch beyond this range. And so the HH is valid to within a drop or 2 of the beginning and the end. And so the HH we'll use over a wider range. Almost to the equivalence point. All right, so we're going to just do some calculations in the buffer region. Pick another volume in the buffer region. What do you want to go with? 9 milliliters. All right. 9 milliliters. All right, so if I take my 10.0, when I do this, I just start the calculation over. I never build up on the previous calculation. So my previous calculation, we got 474. But what I'm going to do is I'm going to start all the way back at the beginning. And so I'm going to have my original acetic acid here, the 0.100 molar acetic acid. And then here I'm going to add 9.00 milliliters of sodium hydroxide, 0.100 molar. And so altogether, I'm going to end up with not 10, not 9, but 19.00 milliliters. If I end up with 19.00 milliliters, then I have to do step I. Step I is what? What is step I? Solution dilution. So I do my solution dilution first. And so I'm going to figure out what my acetic acid is. This is going to be the initial concentration because this is going to initially react. The acetic acid is going to be a 10 to 19 dilution of 0.100 molar. And so 10 to 19 dilution, what is that? Equal to oops. 10 times 0.1 divided by 19. 1 to 19, actually. So I get 0.05263. 0.05263 molar. Carry at least 1 extra digit. And then the sodium hydroxide, all initial, this is going to be a 9 to 19 dilution. 0.100 molar. So let's just do 9 to 19 dilution. 9 times 0.1 divided by 19. Oops, do that again, screw that up. .04738 molar. I probably only want to go 5 decimal places. Let's get rid of that 8. All right, so I do my step I first. Step I. And then I go to step 1. Step 1, what's step 1 going to consist of? It's always the same. What is it? Strongest acid plus the strongest base. What's the strongest acid? Acetic, the strongest base, sodium hydroxide. What's going to make sodium acetate and water? Well, water is pure liquid. And so initial 0.05263 molar, and sodium hydroxide is 0.04736 molar. Do you see we have excess acid? We don't have enough base to neutralize all that. We have excess acid. What's K for this? Very, very large. And so this is going to be minus 0.04736. The limiting reagent is going to completely react. It was 0 molar sodium hydroxide. We have 0.04736 molar sodium acetate. And then this, we'll have to subtract that. 5263 minus 4736. 5263 minus 4736. 527. Now, looking at this, you see this here? You should recognize this as a HH buffer. Even if we took the strongest acid plus the strongest base as acetic acid plus sodium acetate, it's going to yield the same thing. So we take the next strongest acid. Well, the next strongest base, you know, so it'd be acetic acid plus the next strongest base would be water. We go to Ka. But we could save all of that work by just recognizing this is an HH buffer and then just use the pH is equal to the pKa 4744 plus the log of the base is 0.04736 over the acid 0.00527. So let's go ahead and do that. Minus 0.95. No, plus 0.95. So this is 4.744 plus 0.953. Which gives us 5.697. 5.697. And so the pH at 9 milliliters here will be 5.697. 5.697. All right, this is your standard calculation. Your standard calculation is we're given a certain number of milliliters, we have to figure out what the pH is. Now we're going to look at some alternate calculations. One of the alternate calculations is this. An alternate calculation would be how many milliliters would it take to hit a certain pH? Well, that's not too difficult in the buffer region. And so let's take a look at that here. Let's say if I wanted to figure out how many milliliters would it take to get to pH 3.2. So I'm at 287. Let's say how many milliliters will it take to hit a pH of 3.20. And so let's look at some alternate calculations in the buffer region. I have to be in this buffer region between 0 and 10 milliliters. And so, and then I know the pH. The pH is going to go from 287 to, actually, let's figure out what this pH is here. And so that's going to border the buffer region. So let me just we'll do that. Well, the pH, you know, it's going to be, actually, it's going to be completely neutralized. If I completely neutralize this, the pH is going to be greater than 7 because I'm going to be left with sodium acetate. So this pH is greater than 7. I'll calculate it a little bit later. But one alternate calculation here is, let's say I have a pH of 3.20, and I want to figure out how many milliliters of sodium hydroxide will that take. All right. And so how do I do that? Well, the thing is here, I'm going to be in the buffer region. Here. So if I'm in the buffer region, then if I have a pH that's going to be 3.20, this is going to equal the pKa plus the log of the acetate to acetic acid concentration ratio. And so this is going to equal 4.744 plus the log of the ratio. And therefore, the log of this ratio is equal to 3.20 minus 4.744, which is 1.544 negative 1.44. And so the ratio, the acetate, we'll just take the anti-log. Acetic acid is equal to 10 to the minus 1.5, which is going to equal 0.028. All right, now this is the ratio that I have. And what does this ratio mean? This ratio means that I'm going to have 0.02857 parts of acetate for every 1 part of acetic acid. This is the ratio that I need at the end of step 1. Okay, so what we'll do is we're going to set up the ice table here to try to figure it out. Because at the end of step 1 is acetic acid plus the strongest base present, which is sodium hydroxide. It's going to yield sodium acetate plus water. And so here, at the end of step 1, I need this ratio. I need 1 part of acetic acid for every 0.02857 parts of sodium acetate. Okay, so that means what did I have at the beginning? So I have to work backwards. Okay, can you work backwards in this ice table here? Working backwards, that means I must have started with 1.02857 because I must have had 0.02857 here because I started off with 0 here. Do you see that? And so what this means is this. This means I started off with a total amount of acid of 1.2857 parts, and I've neutralized 0.02857 parts of that. What this means is and this is what I'm at the 0.02857 out of 1.02857 equivalence point. And so we have different names for this. If I'm at this 10 milliliters, I call that the equivalence point, because I'm at 10 out of 10 parts of the way. If I'm at 9 milliliters, I call that the 9/10 equivalence point. At the 9/10 equivalence point, I'm 9/10 of the way to 10 milliliters. And the 9/10 equivalence point. And so do you know what this is here? Do you know what 9/10? Take a look at it and see what is 9/10 of 0.05263. And so just go 0.05263 times 9 divided by 10. Screwed up. Okay, let me try that one more time. Did somebody do that? 36. Do you see that? If you take 9/10 of 0.05263, do you know what that is? That's 0.04736. And so what this means is this is enough sodium hydroxide to neutralize 9/10 of my acid. So what's 1/10? Well, this is supposed to be 1/10, but because of round off error, it doesn't come out 1/10. So I have 1/10 of my acetic acid left over, and 9/10 of it has been converted into conjugate base. Well, it's the same thing here. What I'm going to do is I've neutralized, this is 10/10 of it, so I've neutralized this much. And so I've neutralized 0.02857 out of 1.2857 parts. And so then what I'll do is I'll take that and then times it by 10 milliliters, because 10 milliliters would be the full amount. And therefore I go 0.02857 divided by 1.02857 times 10.00 milliliters. And what does it give me? It gives me 0.02857 times 10 divided by 1.02857. Using 0.277 milliliters. And so by the time I hit 0.277 milliliters, or about 0.28 milliliters, I'm going to be at a pH of 3.20. All right, so this is probably confusing, this equivalence point stuff here. So we're going to look at the next alternate calculation. Let me erase some of this stuff. the next series of alternate calculations, so these are shortcut calculations. We're going to go from the equivalence point, the x equivalence point, to the pH by doing this. And so there are going to be some ones that are going to be very quick and easy to do. At 5 milliliters, we call this a half equivalence point because we've added half as much base as required. Full 10 milliliters required, we added half of that. It's a half equivalence point. And then we have the 1/4 equivalence point and the 3/4 equivalence point. The 1/4 equivalence point will come at 2.5 milliliters. And the 3/4 equivalence point will come at 7.50 milliliters. Here. And then we're going to have the 1/11 equivalence point here. And the 10/11 equivalence point here. These ones are very quick and easy to do. We'll start off with the half equivalence point. And so at the half equivalence point, we don't even bother doing the solution dilution with step I. We can skip that. Because at the half equivalence point, this is what we're going to have. If I look at my acetic acid, this is optional because you can just do this in your head. If I look at my acetic acid and the sodium hydroxide, I'd neutralize half of it. So sodium acetate and water. And so let's start off initially. I have some, and it can be any amount of acetic acid initially. And then I'm going to neutralize half of it. And so I'm going to add some sodium hydroxide. The sodium hydroxide initial is going to equal 1/2 the acetic acid concentration initial. Because we're going to neutralize half of that acid. And then this is going to come out 0. And so at the end of this, I'm going to have half of my acetic acid left over. So half of it won't have been neutralized. I'm going to have 0 molar of this, and then I'm going to have half, the sodium acetate, I'll just write it out, the sodium acetate that I'm going to end up with is going to be 1/2 the acetic acid. This is just based on the stoichiometry of this. And so I've neutralized half my acid, so I have half left over, and that half was converted into sodium acetate, which is the base. You see this is a Henderson-Hasselbalch with a 1-to-1 mixture of acid to base. And so this is going to be pH is equal to the log, 4744 plus the log of this. Well, it's 1/2 HIC over 1/2 HIC, which is just 1. Log of 1 is 0. And so the pH is just 474. And so what we do here is, you don't really even have to do this calculation. For weak acid, strong base, the pH at the half equivalence point is equal to the pKa at half equivalence point for weak acid, strong base titration. And that's for this titration. The half equivalence point. So we're going to do the other ones in an even shorter manner. And so let's look at the 1/4 equivalence point. The next example is the 1/4 equivalence point. What does a 1/4 equivalence point mean? It means you've neutralized 1/4 of your acid. Okay, so what I'm going to do is I'm just going to go straight to the Henderson-Hasselbalch. pH is equal to pKa plus now the log. The top is the base. The base comes from how much an acid you've neutralized. I've neutralized 1/4 of my acid, therefore I have 1/4 parts of base. How many parts of unreacted acid do I have left over? I have 3/4 left over. And so what I'm going to do is I'm going to get this. The pH is equal to the pKa plus the log of, the 4 drops out, the log of 1/3. The log of 1/3 is the acid to, base to acid ratio. The log of 1/3 is minus 0.47, as I recall. Let me just double check that. Minus 0.477. So this is pKa minus 0.477. And so at the 1/4 equivalence point, I have the pKa minus 0.477. And let's go to the 3/4 equivalence point. If I go to the 3/4 equivalence point, then it looks like this. At the 3/4 equivalence point, I know I'm in the buffer region, so this is pH is equal to pKa plus the log of, now, how much base do I have? The amount of base I have is 3/4 parts because I've neutralized 3/4 of my acid, I produced 3/4 base. I have 1/4 acid left unreacted, so that's the remaining acid. And so this is the 3/4 equivalence point here. And this is going to equal the pKa plus the log of 3. The log of 3 is plus 0.477. And so at the 3/4 equivalence point, I have the pKa plus 0.477. That's that. All right, so this is it. This is what we call the equivalence point here. It's in the numerator. That's the equivalence point. There. This is the base to acid ratio. Note the relationship between the equivalence point and the base to acid ratio. Over here, this is the equivalence point here. And this is the base to acid ratio of 3:1. Again, note that the relationship between the equivalence point and the base to acid ratio. This is why I'm doing 1/11. Now, why do 1/11? 1/11 is a little strange, isn't it? And so the 1/11 is the easiest because no calculations required. Do you know what the pH is at the 1/11? This is so easy. The pH at the 1/11 equivalence point is, well, first is, how many mils is 1/11 of 10? And so the 1/11 would be 1/11 of 10 milliliters. And so 1 times 10 divided by 11. So 10 over 11, oops. It's 0.909. And so this is, 1/11 equivalence point is 0.909. 0.909 milliliters if 10 is mine. And so I know what the pH is. The pH is so easy. At the 1/11 equivalence point, the pH is the pKa minus 1. And the 10/11 is so easy. Well, what's 10/11 of 10 milliliters? 10/11 of 10 milliliters is 9.09 milliliters. So at 9.09 milliliters, the pH is really easy. At 9.09 milliliters, the pH is pKa plus 1. And so those turn out to be very simple here. Now, why does it come out that way? We just go straight to it. Let's go to the 1/11 equivalence point. If we go to the 1/11 equivalence point, the pH is equal to pKa plus the log. 1/11 neutralized, 10/11 unreacted acid. And so this is going to give me the pKa plus the log of what? 1/10. Well, it's a 1 to 10 ratio of base to acid. That's just going to be the pKa plus 1, minus 1. See that? And so note the relationship between the equivalence point and the base to acid ratio. This is the opposite. This is 10 to 1. Yeah. And so I got to stop here because we're out of time, but I'll continue next time.